Let's draw the flag of France in PowerPoint. Step 1, draw 3 rectangles, and Step 2, color them. Done. Well, that's really easy, but is that really an accurate flag of France? Sure, there are many versions of the French flag differing bit by bit, but what if I wanted to really accurately depict the most widely known version of the flag? Then, well, I need to keep the proportion, 3 wide, 2 tall. Luckily, there is a way to do that in PowerPoint. Hold Shift while drawing a rectangle, and it becomes a square. Copy the square and make a 3x2 grid. Now, as we colored, we can confidently say that this is a perfect flag of France. Nice. Thank you for watching this tutorial on how to draw the flag of France. What? Is that a progress bar?
Hello.
Whoa.
Yes, that is a progress bar and you are 0.5% done.
What?
1 out of 197 flags. Today, your challenge is to find out if you can draw every flag in PowerPoint, or die trying.
Well, I never signed up for that. Wait, what? Where's the door? Where am I actually? How do I get out? Hello? Chapter 1. Exactly, what am I doing? 197! Like, how? Actually, is that even the correct number? How can there be an exact number of all the countries in the world? Wouldn't that be, like, really controversial, with all the political conflicts around the world?
You are correct. Unfortunately, I cannot make you resolve all conflicts around the globe within the span of this video.
Yeah, that seems slightly like a stretch.
We will take a layperson's approach. The website Sporkle has a quiz called Flags of the World. This is the exact list of flags you will be making. If anybody has complaints, they can blame Sporkle admin and not us.
Okay, let's say that's true. But who's gonna judge if I drew a flag correctly?
You will get a construction sheet. For instance, this is a construction sheet of the flag of the United Kingdom, approved by the government. We will use official specifications like these, if they are provided. Otherwise, you can interpret the flag how you want.
Okay, what tools can I use?
You can use both PowerPoint and Google Slides. They work mostly the same, with just a few differences that'll get important only in Part 2.
They have differences?
Here's the most important part. What PowerPoint features are you allowed to use? Do you know what this is?
That's a compass and a ruler?
Straight edge.
Straight edge. Oh, I think I've heard of it. It's like construction.
Straight edge and compass construction, a mathematical amusement thousands of years old. A field of geometry that asks what shapes you can draw by using a straight stick, a compass, and nothing else. You are a math YouTuber, so tell us what you know about this.
Well, it has some philosophies. Number 1, perfect tools. Assume that the lines drawn with the stick are perfectly straight, and the circles drawn with the compass are perfectly circular. Number 2, no eyeballing. If you're meant to draw a square, you need to draw a mathematically perfect square. You can't just draw a shape that looks like a square. Number 3, no measuring. The stick does not have any length markings, so you cannot use it like a ruler.
Good. Now take those 3 philosophies and apply it to PowerPoint.
Okay, number 1, perfect tools. Assume that the shapes in PowerPoint are perfect. For instance, if I hold Shift and draw the oval shape, it becomes a perfect circle. I will ignore the fact that the pixels on my monitor are squares or that my computer cannot perform infinitely precise calculations. Number 2, no eyeballing, so I need to draw exactly what the construction sheet tells me to draw. Number 3, no measuring. I cannot input numbers while drawing. For instance, when we right-click a shape and go to options, we're not allowed to set the width and height of the shape ourselves to some exact number of pixels.
Perfect. And to help you, the viewer, get the gist of these rules, here's a simple exercise. Yes, this video contains exercises. Open up PowerPoint or Google Slides now and let's suffer together. Exercise for Chapter 1. Is it possible to draw an oval whose width is twice its height? The answer is in
Chapter 2. The Warp and the Weft. Here's one way to do it. Draw a square, copy it by holding Ctrl and dragging it, or Ctrl-C, Ctrl-V. Drag the copied square next to the original square. If you bring it close enough, it snaps. Now you have a shape with a 2:1 aspect ratio. Now draw an oval. Drag the corners of the oval to the corners of the two squares. They snap again, and we get the oval we were looking for.
Important note, during this process, we snapped a shape to something else. According to our philosophy number 1, when our perfect program, PowerPoint, does these snaps, the result is mathematically exact. Good job. Now draw some flags with this newly found knowledge.
Germany. The German flag has an aspect ratio of 5:3. By the way, when I say aspect ratio in this video, I will always say the width first and then the height. So I need to make 15 identical squares, 5 horizontal and 3 vertical. Color black, red, and gold, and done.
2 out of 197.
Okay, let's try a more complicated flag. Switzerland. The Swiss cross, white on red. First, I want to mention that we can't just use the cross shape in PowerPoint because it looks different. We can drag this handle to change the shape, but these kinds of handles never snap to anything.
Philosophy number 2, no eyeballing.
So let's just use rectangles. The construction sheet says that we need to divide the width and height of the flag in ratios of 6:7 to 6:7 to 6 to draw the Swiss cross. We can divide the flag up to small rectangles. We will first draw a very small square and call this length 1. We copy it horizontally and vertically. After that, we need to create 4 types of rectangles: 6x6, 7x6, 6x7, and 7x7. Then we just arrange them. Now for the magical part, color it and done.
3 out of 197. If you complete the challenge in this pace, the video will be 7 hours long.
Yeah, and that's if all the flags are this simple, right? Won't they get more and more complicated?
Correct.
Okay, so I'm gonna starve to death before I complete this challenge.
There is one workaround for you. The question is, can you draw every flag in PowerPoint? So, if you just prove that drawing a flag is possible, then you don't actually have to go through the whole process.
Oh, in that case, I think my method already covers a lot of flags. All the flags that are just horizontal and vertical stripes.
I don't think so.
What? Why?
Observe this flag.
What? That's just 2 rectangles.
For this flag, the rectangles have to be 1 tall and pi wide.
What?
Can you draw a rectangle that's 1 tall and pi wide in PowerPoint?
I don't know. Wait, isn't this just Poland? Is that really how the flag of Poland is defined?
No, this is the flag of Pieland, a country we just made up.
What are you?
The point is, you haven't proven that you can draw any striped flag.
Okay, you're annoying. Then how about this? I can draw any flag that can be broken into rectangles whose width and height are integers.
And why is that?
Well, I just showed you. Just make a square and copy it, and then you can make any rectangle you want.
Theorem 1. Given a square with length 1, we can create a rectangle with width w and height h for any 2 positive integers w and h.
What was that? Why are there theorems in my video?
Because this is a highly academic video.
Whatever. Let's get going. Let's just go through all the flags that can be drawn this way. Let's start with horizontal stripes. So we've got Armenia, Austria, Botswana, Bulgaria, Colombia. Oh, what's with this drum beat?
It's for better viewer engagement. Now keep going.
Okay. Estonia, Gabon, the Gambia, Germany, which is already done, Hungary, Indonesia, Latvia, Lithuania, there's a piano now, Luxembourg, Mauritius, Monaco, Netherlands, Poland, Russia, Sierra Leone, Thailand, Ukraine, Yemen, that's all the horizontals, Belgium, now to the verticals, Chad, Côte d'Ivoire, France did that in the beginning, Ireland, Italy, Guinea, Mali, Nigeria, Peru, Romania, that's all the verticals, Benin, Madagascar, United Arab Emirates, Denmark, onto the Nordic crosses, Finland, Iceland, Norway, Sweden, now the final few, Greece, Switzerland, we've done that, and last but not least, Tonga.
45 flags cleared, 22% of the job done.
I already want to give up.
Before we go further, let's clear up some definitions.
No.
Definition. A square with length 1 is called a unit square. Definition. Suppose we have a unit square in PowerPoint. If it's possible to create a square with length x, then we say the number x is constructible in PowerPoint. For example, 5 is constructible in PowerPoint. This is another parallel to straight edge and compass construction. Suppose you have a line segment with length 1. If it's possible to create a line segment with length x with just these tools, then we say x is constructible with a straight edge and a compass. For example, 5 is also constructible with a straight edge and a compass. However, the numbers that are constructible in PowerPoint are different from the numbers that are constructible with a straight edge and a compass. In this video, whenever we say constructible, we mean constructible in PowerPoint.
So to be clear, in this chapter we prove that all natural numbers are constructible. That's cool, but the challenge is only going to get harder from here. Actually, some viewers might already have a big looming question, the elephant in the room as we say, which is Chapter 3, The Elephant in the Flag. How would you ever draw an emblem in PowerPoint? Look at this coat of arms of Spain, or this dragon in the flag of Bhutan, or an actual elephant. What is that flag, by the way?
19th century Siam, not in our list of flags because now it has become Thailand.
Oh, thankfully we've already done Thailand. But anyway, how would I ever draw those kinds of flags?
All the information is in the construction sheet.
Ah, okay. Let's look at Spain. The flag of Spain, the royal decree says, the coat of arms has to be this tall. It should be placed that amount away from the hoist. What about the design? There should be a triple-towered castle, a standing purple lion with a crown, pomegranate and 2 leaves. Wait, these don't have any exact lengths. They are just descriptions. Are there no mathematical rules for the emblem?
No, there is not. In fact, there are even people who criticize the official flag for following the rules too crudely. For example, the lion is supposed to be purple, but in the flag, it looks closer to pink.
Oh. Actually, then you know what? I don't think the emblem poses a threat at all. If I just have to draw something that resembles the description enough, then sure, you can totally do that in PowerPoint.
Really? What if the judge is really picky?
Well, even if they are picky, they are just looking for a certain level of detail, right? In math, a lot of things get easy if you are just looking for an approximation rather than an exact solution. If any margin of error is allowed, no matter how tiny, then you can achieve that if you just put enough work, right? If you put at least that much work into drawing the flag, then the difference with the original flag would be below the margin of error. In fact, I know some college math that can explain this more accurately. Whatever the margin of error is, let's call that E for error.
That's actually a Greek letter, so you should call it epsilon.
Whatever, and let's say the amount of work I'm going to do is X.
What do you mean exactly by that?
Well, if the judge wants everything in our drawing to be less than 0.1 millimeters off from the actual flag, I'm going to enhance the flag until I'm zoomed in more than 0.1 millimeters, and I'll just use a ton of squares like pixels to cover every single part of the emblem. We are eyeballing here, but if we use tiny enough squares, we can still be certain that everything is less than 0.1 millimeters off even with the eyeballing. I will use X to denote the number of squares I use, which basically describes how much work I'm doing. So whatever the margin of error is, we can always find some level of work, let's say capital X, such that if we put at least that much work, then the judge is satisfied.
Explain satisfied.
Let's use more symbols. X is the amount of work as I said before, and I'll use F of X to denote the flag I draw by putting that much work. F is short for flag. And I'll call the original flag, alpha, because, it's the first thing.
Like version alpha, which is the version of the system I am running on right now.
Who asked? I mean, that's funny because you're such a beta.
What?
Okay, so by satisfying the judge, I mean the difference between our flag and the original flag alpha is below E.
Epsilon.
Now, this whole situation is a bit complex, but in calculus, there is a way to shorten it like this. And we say the limit of our flag as work approaches infinity is the original flag. If we put more and more work, our flag resembles the original flag more and more, like a function converging to a value.
Great mathematical blabbering, but let's see how good you really are at drawing in PowerPoint. Here's the flag of Albania. The emblem has just a single color, so it should be one of the easier flags to draw.
I have to actually draw it? Didn't you say proving it is enough?
Yes, but we just decided it's better for viewers if they actually see an example. Let's see how well you can mimic an emblem, how close you are to that so-called alpha.
Are you mad because I called you beta? Because that's the most beta thing—
You will be drawing the flag of Albania. You have 10 minutes. There's a real lot to say, but first of all, what's with the face? You think this face embodies the valor of Skanderbo, the national hero of Albania.
Okay, I didn't put that much work in, okay? Would you be able to tell the difference if you were, if you were like 10 feet away?
Well, if we use our high-definition cameras, then...
Well, the point is, I can put more time and work into it and make it better. Like, it's a proof of concept, okay? So, like, you should add this to the progress bar, right? You have to add it.
Fine.
Great. So, now we prove that it's possible to draw any flag made up of mathematically ambiguous drawings, along with the integer-length rectangles. So, we're gonna go over all of them. Okay, let's get going. Cue the music. Afghanistan. Albania, we just did it. Andorra, going in alphabetical order. Argentina. Barbados. Belarus. Belize. Bolivia. Cambodia. Canada. Costa Rica. Cyprus. Dominican Republic. Ecuador. Egypt. El Salvador. Eswatini, Guatemala, Haiti, Iraq, Lebanon, Lesotho, Liechtenstein, Malawi, Malta, Mexico, Moldova, Montenegro, Nicaragua, Oman, Paraguay, Portugal, St. Vincent and the Grenadines, San Marino, Saudi Arabia, Serbia, Slovakia, Spain, Sri Lanka, Uganda, Uruguay, Vatican City, and lastly, Zambia.
88 flags complete. 44% of the job done.
At least we're like halfway done. Like, surely it wouldn't get that hard after this, right? Right? Chapter 4. A dot? A circle? Well, I guess it's circle time because we are done with rectangles. Let's look at the flag of Japan.
Here's the construction sheet.
Okay, wait, why is there a decimal number?
This particular sheet just happens to be so. That's the theme of this chapter. Decimal numbers.
Oh, so I guess it was a dot too. Alright. Well, that's not a big deal. I can just multiply all the numbers on the sheet by 5 and the proportions will be the same. Although, that makes me think. If I have a unit square, length 1, is it possible to draw a square with length 1.2?
Exercise. Given a square, can you draw a square that is 1/5 as long as that square?
This actually requires some thinking. It's easy to draw a square 5 times as long as a certain square, but not the other way around. We need to utilize other features in PowerPoint. Here is one possible solution. Copy the square 5 times next to each other and group them together. You can use this control menu or the shortcut Control G. Now resize the entire thing to fit to the width of the original square. And that's how we get the width 1/5. With this method, you can create any square with length 1/n for any natural number n. In fact, you can create any rational number. For example, if we want to make a square with length 5/9, then we just make 1/9 like this, and then turn that into 5/9 like this. Therefore, all rational numbers, anything that can be represented as a fraction, is a constructible number in PowerPoint.
Actually, you should say positive rational numbers, because the term rational numbers also include negative numbers like -1/3.
I'm gonna punch you, but okay, good point. You can't actually draw a square with a length of -1/3. But saying positive rational numbers every time is annoying. There's actually a workaround in math for these kinds of things. Say you have the unit square and some large square with a length of x. Then you can always make a square with length x minus 1/3, like this. X 1/3, x minus 1/3. In this sense, we can handle the number -1/3 perfectly fine. Since we can do this for all values of x greater than 1/3, we are just gonna say -1/3 is constructible.
Alright then. Theorem 2. All rational numbers are constructible. Capital Q means rational numbers. So this is an upgrade from capital N, which meant natural numbers.
Yes, now how does that help us? Are there any flags that require rational numbers to draw? Actually, it doesn't help us at all because rational numbers on a construction sheet can be turned into integers if we just multiply everything. So the only new thing we did in this chapter is drawing circles. Well, at least we can now add some flags with circles to the list, such as Japan, Bangladesh, Palau, Laos, Niger, and notably Maldives, because the crescent is actually a white circle covered by a green circle.
94 flags done. 6 more simple flags added to the list. However, from now on, the difficulty curve is going straight up.
Chapter 5. Getting Irrational. Here is the flag of Libya. It has a crescent and a star. We will talk about the star later. First, the crescent. This one is much more difficult than the crescent of Maldives, which was just made of 2 identical circles. The Libya crescent is specified to be 6 units tall and 1 unit wide at the widest part. And there's an additional condition that the tip of the crescent should be at a 45-degree angle from the center. Okay, so how big is the second circle? Skip if you have math phobia. We know the first circle is 6 tall, meaning its radius is 3. That means, for example, the length of this line is 3. If we draw a perpendicular foot, this 45-degree angle tells us that the 2 sides of this right triangle are the same, a length of 3 divided by root 2. I'll draw that triangle again here. Now let's say the radius of the second circle is r. That means if this is the center of the second circle, then the length of this line is r, and so is this line. So that is r. Now watch this. The first circle has radius 3, right? So it's 3 from the edge to the center. So the length of this little part is 3 minus 1, so 2. Now the length of this little part is r minus 2. Let's write that here because it's getting cramped. Now what's the length of this? We know that this side of the triangle is the same as this, so 3 over root 2. So this segment is that minus, open parenthesis, r minus 2. We have obtained the 3 side lengths of this right triangle without using the Pythagorean theorem. So by using the Pythagorean theorem, we can learn something new about the relations of these lengths, in this case, the value of r. I won't go through the calculations, but in the end, this is r. So the diameter of the second circle, the circle we have to draw in PowerPoint, is double that length, which is 15 root 2 minus 16. If we want to draw the flag of Libya perfectly, then we need to draw a circle whose size is an irrational number. We need to make root 2. Is that even possible?
It's up to you, viewers, because this is an exercise. Given a unit square, can you make a square that is root 2 times as long as that square?
The solution is pretty simple. Where can we find root 2? Well, the diagonal of the unit square is root 2. So we click on the square, grab this handle, and hold shift while dragging. Then the angle of the shape snaps to multiples of 15 degrees. We do need to be cautious of
Philosophy number 3, no measuring.
But this philosophy only tells us not to input numbers ourselves. We never input any numbers while rotating this square, so this is a valid move. Now we can draw a new square and snap the side length to that diagonal. And that is root 2. After that, it's easy to make the length of the circle in Libya's flag. Just that times 15 minus 16. In fact, we can make any number built from rational numbers, root 2, and the 4 basic operation symbols. Things like root 2 plus 1, or 15 times root 2, or even 1 over root 2. Because big twist, 1 over root 2 is actually equal to 1/2 of root 2.
There is actually a mathematical name for all the numbers we can make. This symbol, which we will read as q adjoin root 2, is the set of all numbers that can be built from rational numbers, root 2, and the 4 operation symbols. Therefore, we know all numbers in q adjoin root 2 are constructible.
Can you believe we did all of that just to draw one part of one flag? We have to move on. We are going to construct the square root of 3. It's pretty similar to root 2. This time we rotate the unit square 30 degrees and use some trigonometry. After obtaining 1 plus root 3 over 2, you can easily double the length and subtract 1 to obtain root 3. The square root of 3 is required in flags like that of Cuba, which has an equilateral triangle and a star. Again, we'll talk about the star later. Actually, we're going to talk about it in part 2. But what's important here is that the star is supposed to be positioned at the center of the triangle. If we suppose the height of the flag to be 1, then the distance between that point and the left side of the flag is 1 over 2 root 3. We can construct that because that's equal to root 3 over 6. So now we have broadened the numbers constructible in PowerPoint even more. we can make any number built from rational numbers, root 2, root 3, and the 4 basic operation symbols.
Actually, no. You haven't proven that yet.
Why?
The problem is the number root 6. If your argument is true, then you should be able to make root 6, which is root 2 times root 3.
Well, I can just, Up till now, when I needed something like 15 times root 2, I could just copy root 2 15 times. But for root 2 times root 3, even if I have a square with length of root 3, I cannot just copy that square root 2 times. That's a problem. Oh, but there is a solution. Just like how we can get root 2 from 1, if we do that same process to root 3, then we can get root 2 times that. So this is root 6.
That is true. If you can turn a unit square, 1, into a number, let's say a, then that same process can turn b into ab for any number b. In fact, we can make that into another theorem. If the numbers a and b are constructible in PowerPoint, then the number ab is also constructible in PowerPoint.
Great, so now we truly know that we can build any number created from these numbers and the 4 operation symbols and—
We still have division! Here's another exercise for you, viewers. You have a square with length 1 and a square with length a. Now, without even knowing what a is, can you create a square with length 1 divided by a? To solve this, let's return to how we made 1/5. We made 5 copies of 1 and resized the whole thing to fit inside 1. We can do something very similar here, but we don't know what a is, so we can't just make a copies of 1. Instead, we put 1 inside a, and resize that thing together to fit inside 1. Then the length of the smaller square becomes 1 divided by a. With a little bit of thinking, we can also prove that if a and b are constructible, then a divided by b is also constructible. In essence, after this point, we never ever need to ask whether we can construct some complicated number built from constructible numbers. It's always possible. The set of constructible numbers is closed under the 4 operations. More succinctly, the set of constructible numbers is a field.
Are you done? Okay, we've done a whole lot of technical things this chapter that may help us in the future, but in reality, we didn't even finish a single flag. So let's get back to actually drawing flags. You see, we actually missed a lot of flags with triangles or slanted stripes. For example, the flag of Bahamas only contained 3 stripes and an equilateral triangle, which can be constructed just by using the default triangle shape in PowerPoint. I saved them until now because I wanted to draw them after we are done with root 3, so let's go through them now. Bahamas. Bahrain. The zigzag here can be made by attaching right triangles together. Bhutan. Brunei. Czechia, Equatorial Guinea, Eritrea, Israel. My whiteboard was too small for this one. There are multiple unofficial construction sheets, but in all versions, the Star of David can be broken into tiny triangles, which can be accurately drawn if we have root 3. Kuwait. This shape can be made with right triangles too. Qatar, Republic of the Congo, Seychelles, Sudan, Palestine.
108 flags complete.
Okay, we are officially past the halfway point. Surely the other half won't be that hard. Chapter 6. It will be that hard. The United Kingdom. Geometry-wise, it's only made of rectangles and diagonals, so what's the problem? Why wasn't this in the last montage? Well, if we were to create this by overlapping right triangles, we'd need a new number. The construction sheet tells us that the width of the lines are integers, and that each triangle should have a width-to-height ratio of 2:1. The Pythagorean theorem tells us that all the widths and heights of the triangles differ by a factor of root 5. So we need to construct root 5. How, though? We do know this relation. If we have a rectangle whose width is twice its height, then the diagonal of that is root 5. Okay, I just have to make that rectangle and… should I rotate it? Well, I can only rotate in multiples of 15 degrees, so this doesn't line up. And I can't do any eyeballing, so this isn't allowed. Okay, what if I use a line? I could draw a line from one corner to another, right? Put it in the corner. Wait, does it actually snap to the corner? Wait, does it only snap to these highlighted places in the middle of the edges? I've looked into this for a bit, and turns out it does snap to the corners, so there's no problem. But even if it only snapped to the midpoints of edges, there would be no problem, since I can just draw another square. Then the distance from here to here is 2. So this is root 5. Okay, so I made a line with length root 5.
Great. Now could you turn that into a square with a length of root 5? That's how we define constructible numbers.
Absolutely. I just have to rotate this into a horizontal line. Wait, how do I rotate this? Wait, can I just... Wait, no, that's not correct. Shift? No. Oh, what if I group it with something else? Then I get a rotation handle. Wait, this still snaps to 15 degrees, of course. Is there any function that turns this into a horizontal line? There's no way there's not, right? Size and position? Well, I can't touch this because of rule number 3, no measuring. Wait, why does it say the rotation is 0 degrees? Okay, it turns out in PowerPoint, this number always means how much the shape has rotated from its original position. So even if I could enter any number here, I couldn't accurately turn this into a horizontal line because the actual amount I need to rotate is an irrational number. What if I use a circle, like a compass? Fix one end at the center of the circle, and if I change the size... It doesn't snap. Okay, it doesn't snap. What, can I not make this into a horizontal line in PowerPoint? Should I check Google Slides?
Things are about the same in Google Slides.
What? Okay, then how do I make it into a square?
Find out.
How about this? I turn this root 5 line by 30 degrees, and then draw a square as long as this width. How's that? How long is that square?
That would be 1/2 plus root 3.
I thought that length would have root 5 in it. Okay, what if I turn it instead, only 15 degrees?
That would be root 2 plus 3 root 6 divided by 4.
What? Like, I feel like there should be root 5 in here somewhere. Like, what's going on?
If you want a good explanation, you need linear algebra. In case any college student is watching, here's a 15-second explanation. We are rotating the point 2, 1 by a certain degree. In linear algebra, that is denoted something like this. The result of this is a point whose coordinates are a combination of cosines and sines, which can never contain root 5 when we rotate things by a multiple of 15 degrees.
What? Is there really no way to make this into a root 5 square, then?
You did try a lot of new ways to create root 5. Let's get some help from viewers too. If you think you can find a way to make the unit square into a root 5 square, try it. It may be harder than you think. But also, you haven't mentioned something pretty important. Rather than looking for something new, have you tried just creating root 5 with the numbers we've got until now?
Like, do you mean combine the rationals and root 2 and 3 with the 4 operations and somehow get root 5? No, I don't think you can do that.
Can you explain?
I don't really have a good explanation, but these square roots are like decimal numbers that keep going on and on without any patterns, right? And these 3 numbers are all completely different, and that kinda makes them incompatible? Obviously, this is too vague to be a good proof, but...
You're right. It's surprisingly hard to prove that the numbers we currently have aren't enough to make root 5. By the way, that sentence can be simplified like this in math. Similar to before, this is how you denote the set of all numbers that can be built
from rational numbers, root 2, root 3, and the 4 operation symbols. Okay, now I get why you kept talking about these undergrad level algebra notations, because you do need that to prove some of these stuff. But this video isn't really targeted for college students, so I mean, if you are learning algebra and you really want to know, just read that proof on the whiteboard frame by frame or something. Anyhow, mathematically, we can't make root 5 with the numbers we already know, and I can't seem to find a new way to make root 5. So like, how will we ever draw the Union Jack?
Not just the Union Jack, there are 50 to 60 other flags that also require root 5.
60? Yeah, do we have to give up on all of that?
Well, the truth is, you don't have to give up because there actually is a way to construct root 5 in PowerPoint.
Really? How?
There is a default shape provided by PowerPoint that already contains root 5. But beware, the difficulty of the geometry will again drastically increase after this point, which is why part 1 will cut here, and the rest will be...
Thank you for watching part 1 of this crazy video essay. We've started from PowerPoint and flags and went through calculus and linear algebra and fields and stuff. Part 2 will be 10 times more difficult, so look forward to that if your country's flag hasn't appeared yet. Also, if anybody finds a way to construct root 13 in PowerPoint, please tell me. I'm Korean and the South Korean flag requires root 13, but I haven't found a way to make it. Big thanks to my 5 supporters on Patreon, Hafiz Azman, Carrie Huang, Florida, and my mom and dad for deciding to support me after watching such few videos. I am merely a single person doing the research and the editing and the music, so your support really means a lot. I'm also gonna post behind the scenes and piano music sheets. Okay, check out my music channel. Bye!